Proof by induction, the method. Consider the sum of the first n odd natural numbers. So when n is 1, so the first term is 1, which is equal to 1. When n is 2, for the second term, 1 plus 3 is equal to 4. So 1 is the first odd number, and 3 is the next odd number, and 1 plus 3 equals 4. When n is 3, so for the third term, 1 plus 3 plus 5 is equal to 9. So 1 is the first odd number, 3 is the second odd number, 5 is the third odd number, and that equals to 9. When n is equal to 4, so for the fourth term, 1 plus 3 plus 5 plus 7 is 16. And when n is equal to 5, so for the fifth term, 1 plus 3 plus 5 plus 7 plus 9 is equal to 25. So 1, 4, 9, 16, 25 represent the sum of the first n odd natural numbers. And obviously this list will go on forever. So, for example, for the first term 1, we just had one odd number. For the second term 4, we had two odd numbers, so n was equal to 2. For the third term 9, we had three odd numbers, so n was equal to 3. For the fourth term 16, we had four odd numbers, so n was equal to 4. For the fifth term 25, we had five odd numbers, so n was equal to 5, and so on. Noting that 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, 4 squared equals 16, and 5 squared equals 25, i.e. the square numbers, and so on. It appears, so it looks like, that we can formulate the rule that the sum of the first n odd natural numbers is equal to n squared. As the nth odd natural number is 2n minus 1, it appears as if we have the formula 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 equals n squared. So just to confirm where this 2n minus 1 comes from, any odd number is a number multiplied by 2 minusing 1, because 2n would give us all the even numbers, because anything multiplied by 2 will be an even number, and if you subtract 1 from any even number you get an odd number. However, on the basis of a few examples shown above, it is not safe to propose that the above formula is always correct. For all we know, the formula may fail for some larger value of n, which we have not checked. To be confident that the formula is always correct, we need to prove it. One method that can be used to prove statements such as this formula is called proof by induction. This is a method that can be used to prove a proposition, written P of n, put forward as being true for all natural numbers n, from some starting number s upwards. For the example above, so the example in the previous slide, the first number for which we want the formula to hold is 1. Thus, we want to prove P of n equals 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 is equal to n squared. For n elements, so for all n values, elements of the natural number set, i.e. s equal 1. The method of proof by induction consists of 2 steps and a conclusion as shown below. Step 1, show that P of s is true, i.e. show that the statement is true for the first number. So in this case, the first number being 1, but it's not always 1. Most of the time though it is 1. So if P of n is equal to 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 equal to n squared, then P of 1 is going to be equal to 1. So the one term, the first odd number is 1, equal to n squared, which is 1 squared. And since 1 squared is 1, and 1 is equal to 1, P of 1 is true. When n is equal to 1, there is only one term on the left-hand side, i.e. the first term. So when 1 squared was 1, we only had one term on the left, so 1 is equal to 1. So P of 1 is true. Step 2. Assuming that P of k is true, show that, as a consequence then, that P of k plus 1 is true. So we assume P of k is true. So 1 plus 3 plus 5 plus ... 2k minus 1 is equal to k squared. So we've basically just wrote out what P of n was, but instead of n, we have k. So we just substitute k for each n. So we assume that P of k is true. So we've assumed that P of k is true. Now we need to show that as a consequence that P of k plus 1 is true. So to prove P of k plus 1, so we take P of n, so 1 plus 3 plus 5, we write it down, 1 plus 3 plus 5 plus ... And instead of 2n minus 1, we have 2 times k plus 1 minus 1. So we've swapped that n for k plus 1. And likewise on the right of the equal sign, we've swapped n squared for k plus 1 squared. So what we did was we just substituted k plus 1 for each n. So now we just have to simplify this. So 2 multiplied by k is 2k, and 2 multiplied by 1 is 2, and 2 minus 1 is 1. So this simplifies to this. So here's the proof. So the left-hand side, the LHS, the left-hand side. So if we take 1 plus 3 plus 5 plus ... 2k plus 1, well, that can be rewritten as 1 plus 3 plus 5 plus ... 2k minus 1 plus 2k plus 1. So this is just the term before 2k plus 1. So we're just adding this in. It's just the previous term to this. So next we're going to put brackets around the 1 plus 3 plus 5 plus ... 2k minus 1. And I've highlighted it here in pink. And we still have the plus 2k plus 1, but that's not inside the square brackets. Now we know from the previous slide that 1 plus 3 plus 5 plus ... plus 2k minus 1 is equal to k squared. In the previous slide, that's by the assumption P of k. So in the previous slide, we wrote down what P of k was. So this swaps for this, and we still write down the 2k plus 1. So now we just simplify, so we get rid of the brackets. So we have k squared plus 2k plus 1. We can factorize, which will give us k plus 1 multiplied by k plus 1, which is k plus 1 squared. And k plus 1 squared is the right-hand side, which is here, k plus 1 squared. So thus, P of k plus 1 is true, assuming that P of k is true. So conclusion. So we write the conclusion that the proposition is now proved. Thus, P of n is true for all n values elements of the natural number set, QED. So this is just Latin to say we've proved what we were asked to prove. So there are 2 steps and a conclusion involved in proof by induction, and every step has to be included. You can't leave anything out, and you must finish with a conclusion. So the following points should be noted about the method of proof by induction. The theory behind the method goes as follows. First of all, step 1 verifies that the proposition is definitely true for the starting number. In this case, s is equal to 1, and it's usually s is equal to 1. Then step 2 establishes a general bridge between the proposition being true for one natural number and it being true for the next natural number. With step 2, we can now say that because the proposition is true for n is equal to 1, it must also be true for n is equal to 2. Applying step 2 again and again, we can then say that the proposition must be true for n is equal to 3, 4, 5, and so on forever. This completes the proof and is illustrated below. So step 1 shows that it is true for n is equal to 1, 2, 3, 4, 5, and so on. But step 2 shows that it is true for k, and k plus 1. Both steps are required to complete the proof. In particular, step 1 cannot be omitted. Step 2 on its own proves that the proposition will be true for the next natural number if it is true for the previous. However, without step 1, the proposition might be false for all natural numbers. Don't assume that the starting number s is 1. It very often is, but it can be different. By the nature of step 2 of this method, we assume that p of k is true. This means that we take it as a fact. We do not question how we know it. In proof by induction, the induction is that we or somebody guesses the formula in the first place. Then the steps outlined above are used to prove mathematically that that guess is correct.